nuclear reactor represents the largest energy to volume ratio in industrial craft portion of Tekkit, outputting anywhere between 40 and almost 600 energy units per tick depending on its composition and internal arrangement. However, the nuclear reactor also represents the most dangerous power supply, able to utterly destroy your compound if it is not built and controlled properly. In this video, I'll show you the basic ingredients required to construct a nuclear reactor, share some key details as to how they function, and finally show you how to ensure that your reactor never goes into meltdown, no matter how poorly you build it. I'll assume a few basic details that anyone involved in Tekkit should already know, but by and large this will be a lowest level instructional video. What you are looking at right now is footage of a singular nuclear reactor which is entirely full of uranium and possesses the full 6 chambers. There is no cooling involved and there is no shut-off method. Currently, as you can see in the video, the only thing that is stopping this reactor from running at all is the fact that I'm stood on a pressure plate at some distance and it is feeding power directly into the reactor, therefore turning it off. In a moment, I'm going to turn it on. I'm going to step backwards off of the pressure plate. The reactor will automatically initiate and will then proceed to explode. This is a demonstration of the damage that will be caused by a reactor that has no overheating off switch. As you can see, a reactor that has no controls becomes quickly unstable and causes a gigantic crater. This is currently filmed in a flat world, so there isn't any particular damage to the underside due to the bedrock layer very close. However, the outer edges are completely decimated. Let's begin with a look at the key ingredients. The first and most obvious requirement of a nuclear reactor is uranium ore, which is used to create the fuel cells that allow the reactor to actually generate power. This ore generates very rarely in the landscape, usually only in singular ores. However, it can be generated through equivalent exchange, but it is extremely expensive and so. In fact, it costs several times the EMC of diamonds. The reactor and its actual components mainly consist of copper, iron, tin, and bronze. All of these can be generated rather cheaply in EMC. Lastly, some of the less vital components are redstone dust, glowstone dust, and lapis lazuli. With the exception of lapis lazuli, redstone dust and glowstone dust are cheap and are classified by equivalent exchange as fuel items. Because of these elements, it is generally advised to have completed a quarry and visited the Nether prior to beginning construction, as these elements are required for many components, though in relatively small quantities. To create the uranium fuel cell of the reactor, we construct an empty cell from 4 tin in a diamond shape, compress the uranium ore in a compressor into refined uranium, and combine the two. The 3 common items used to construct the reactor are advanced alloy, integrated reactor plating, and an advanced electronic circuit. To create the advanced alloy, we combine 3 iron, 3 bronze, and 3 tin to create a mixed metal ingot, and place the ingot into a compressor. To create the integrated reactor plating, we combine an advanced alloy with 3 copper in a diamond pattern similar to crafting a compass or clock. To create an advanced electronic circuit, we combine a regular electronic circuit with 2 glowstone above and beneath it, 2 lapis lazuli on either side, and 4 redstone at each corner. The 3 items used to manage the internal arrangements of the reactor are the coolant cell, the integrated heat disperser, and the integrated reactor plating. To create a coolant cell, we fill an empty cell by right-clicking on water and place it into an extractor. Worth noting is that the coolant cells do not stack, and therefore you need to either keep an eye on the extractor or have an automated removal method in place while this process continues, as they can quite easily become clogged and cease to produce any more. To create an integrated heat disperser, We combine an integrated reactor plate. Beneath an advanced electronic circuit, place 2 copper on either side of the circuit, and 2 coolant cells on either side of the reactor plate. The integrated reactor plating was covered in the previous section. The physical nuclear reactor itself consists of a nuclear reactor block with additional reactor chambers on up to 6 sides. A reactor chamber consists of an integrated heat disperser and 3 integrated reactor plates in a diamond pattern surrounding a machine block with 4 advanced alloy in each corner. A nuclear reactor consists of a generator with a reactor chamber on either side and an advanced electronic circuit above and beneath it, with advanced alloy once again in each corner. To protect your complex from a meltdown explosion, it is recommended that you construct the surrounding environment of the reactor from reinforced stone and reinforced glass. Optionally, a reinforced door is also available. Reinforced stone is made by surrounding a single advanced alloy with smooth stone. Reinforced glass is made by creating an H shape in the crafting table with normal glass and placing 2 advanced alloy in the remaining spaces. Now that you have your nuclear reactor, it's time to cover some important facts about it. Clicking on any of the reactor chambers allows you to access the main reactor inventory, and each additional chamber adds more inventory space to the reactor, allowing for additional fuel cells. Energy can be extracted from the reactor by use of a multiply insulated high-voltage wire. But be careful, however, as higher output reactors can cause even the high-tier MFS units to explode if a high-voltage transformer is not placed between them. Applying a redstone current to the reactor, such as via a redstone torch or lever, will deactivate the reactor regardless of its fuel status. This will be important in the next step of construction. In Tekkit terminology, different reactor arrangements have different terms. You don't need to know the full jargon for these terms, but suffice it to say that a Mark I reactor will never overheat, whilst a Mark V is likely to overheat very quickly and produce dramatically more power. There is also a special classification for a reactor which deliberately overheats in order to create re-enriched uranium cells for use in other reactors, but as this is a low-level instructional, we won't be covering these more advanced topics. As you saw before, we can deactivate a reactor by applying a redstone current. This functionality is vital in automatically deactivating the reactor before it can overheat and go into meltdown. To properly utilize this feature, we need a thermal monitor. This is created by combining an advanced electronic circuit surrounded by reinforced glass with a piece of redstone dust beneath it. The thermal monitor detects the temperature of the reactor hull and triggers a redstone signal when it passes a certain level determined by the user. By default, this setting is 500. But reactors only begin to enter dangerous conditions after reaching a temperature of 8000, at which time it evaporates water blocks in their vicinity. At increasingly higher temperatures, reactors will also cause fires within the vicinity, and then will cause radiation damage to entities, and finally, detonate catastrophically. Thermal monitors must be placed directly next to a reactor chamber or the reactor itself to function, and their temperature threshold can be adjusted by right-clicking on them. Here we have the simplest form of meltdown control, where the monitor triggers before the reactor can even begin to evaporate water, and immediately deactivates it. However, this setup isn't ideal, as the reactor will momentarily cool, reactivate, and trigger the thermal monitor again before it has properly cooled, creating a staggering motion that will produce relatively little power. To improve the control, we need to use an RS latch, available from the Red Power mod of Tekkit, which will take the output of the thermal monitor and then keep the reactor deactivated until we reactivate it manually after it has cooled down. To further improve the system, we can add a second thermal monitor and invert its output into the same area as our previous button. By having the second monitor use a much lower temperature setting, the reactor will deactivate as it overheats, and then reactivate automatically after it has cooled. By using any one of these systems, we can create a nuclear reactor that is incapable of overheating in even the most dire of situations. We can also use the Buildcraft transport pipes to automatically refuel the reactor, extract near depleted uranium cells, and pump ice and other cooling items into the reactor during emergencies. Feel free to experiment with such systems and with the internal arrangement of the reactor, provided you have already created a meltdown control system such as these to prevent disaster. Thank you for watching, and remember, only you can prevent mine trouble. Many sheep were killed in the recording of this video. Fortunately, all of their families then died of radiation poisoning.